So in this lecture, we're going to talk about concepts from physical chemistry that will be required throughout the course. As I mentioned in the introduction, this will be a tablet-based lecture, and I would encourage you, as I write on my tablet, I would encourage you to get your own notebook and write notes in your notebook as I'm writing, to replicate the experience of writing on a blackboard and taking notes from a blackboard lecture. So with that, let's get started. So we're going to talk about, in this lecture, we're going to talk about concepts from physical chemistry. As an outline of what we're going to talk about, first we're going to talk about some basic physical concepts. We're going to talk about how molecular communication works as a physical process. We'll talk about media. We'll talk about chemical reactions. We'll compare how this works as opposed to wireless. Wireless communications. We will talk a little bit about energy. And the concept of energy in molecular communication. And we will talk about the differences between molecular communication and other kinds. Of communication. Subsequently, we'll talk about chemical reactions. So we'll delve in some detail into the physics of chemical reactions. And we'll talk a little bit about things like what is a reaction, what are some basic kinds of reactions. We will talk about an important concept called mass action kinetics. And we will finish with an example called the Michaelis-Menten equation. So with that, let's get started. Incidentally, I'm going to, as with all my notes, I'm going to upload these notes afterwards. So starting with basic physical concepts. So what is the physical environment for molecular communication? What we basically have, so remember the block diagram. So recall the block diagram. We have a message that goes to a transmitter, that goes through a channel, that goes through a receiver, and then an estimated message. Molecular communication is no different. Well, let's firstly imagine how this works in communication that we're accustomed to. So we would have a message, we'd have a modulator, an antenna. The environment, the channel would be free space. Then we would have another antenna, an amplifier, and demodulator. And ultimately, out of the demodulator, we would get the message estimate. So you can see how these systems stack up. So there's your transmitter. You could argue that all of this is the channel because the free space imposes certain constraints on how radio waves can propagate, and the noise, we generally imagine the noise coming from the amplifier. And then the demodulator, that can be thought of as the receiver. And then out of the demodulator, we make an estimate of the message, and hopefully M and M prime are the same thing. Okay, so how to do this? In molecular communication. So we saw some very basic examples in the introduction. So now let's give that a little more physical structure. So my transmitter, so the environment that I would look at would be something like this. There would be a transmitter, shared medium, and a receiver. And what's going on is that the transmitter will release molecules. So in other words, this implies there is a reservoir in the transmitter, or perhaps, if you like, a factory to create those signal bearing molecules. So in other words, somewhere in here, there's a reservoir that contains a lot of molecules. Then using some technique, which we're going to leave abstract for now, but we saw some examples in the introduction. The transmitter is going to select a molecule and release it into the shared medium. So the shared medium is normally a fluid. And what's going to happen is the released molecule will propagate in the medium via diffusion. Sometimes we call this molecular communication via diffusion. Or MCVD. What does this imply? So this implies the molecule that is released will follow a random trajectory until it arrives at the receiver. So we can imagine the receiver is a region in space. And what can the receiver do? The receiver can count. Actually, let me back up. It can not necessarily just count, but the first thing it does is it can do things like absorb detect, and count. It doesn't necessarily need to do any of these things, but these are the sorts of concepts that it can do. So if you imagine this randomly propagating molecule, it can be absorbed on the surface. It can be absorbed on the surface here. So this molecule, as it travels, can be absorbed on the surface over here. It doesn't necessarily need to do that. So this would be absorbing. And we talk about an absorbing receiver. On the other hand, it could be non-absorbing. The molecule could continue inside the receiver. And you can imagine the differences between these two types of receiver. For an absorbing receiver, the most important thing is first arrival time. In other words, the time at which it arrives on the surface. So a non-absorbing receiver, strictly speaking, it's concerned with everything that's happening inside its volume. But the most important thing, it could consider first arrival time. But normally, when we talk about non-absorbing receivers, we talk about the count of molecules within the volume. So that's generally the two ways of doing it. So basically, you can have absorption. That's usually that goes hand in hand generally with detection in terms of first arrival time, or counting, which generally goes along with non-absorbing, and that basically means the count of the molecules within the volume. So we've seen, in terms of my outline for the lecture, we've seen a little bit about comparison with wireless in terms of free space. We've seen in terms of, actually, let's do a little table here. We'll come back to this table, but we're going to compare things like the medium. So in wireless, the medium is free space. Sorry, just imagine a table here. And in molecular, the medium is normally a fluid. Now, there are other ways to do molecular communication, but what I'm presenting you with today are the simplest ways and the most common ways. So there are other ways to do this, and we might talk about them in this course if we have time, but what we're talking about is the most common and the most typical ways of doing this that you encounter in the literature. We can talk a bit about detection of a signal. So in wireless, we talk about the electromagnetic induction of a current. And that's easily detectable. So in other words, an electromagnetic wave that impinges upon an antenna causes a physical reaction, namely a current, to flow in that antenna. In a molecular communication environment, we are looking for either detection or count of molecules, which stems from a chemical reaction. Actually, let me do that a little better. So either way, if we detect the molecules, basically what we're saying is that the molecule is going to bind to some sort of receptor, and that receptor should be able to take action based on that binding. If we're talking about count, what we really mean is concentration. So there are ways of organizing chemical reactions that can transform a certain concentration into downstream action. So either way, detection, the binding of the message-bearing molecule to a receptor, or a count, which is kind of the same thing except larger scale. Either way, we are performing a chemical reaction. We're going to talk a little bit about that later in this lecture. There are other entries here that I want to include in this table, but we'll come back to it. I want to talk a little bit about energy. So in fact, let's go back here and think about energy. So energy is a very significant concern in wireless, and a lot of the work that we do is to optimize systems with respect to their energy expenditure. And normally, I mean, energy is easily formulated in terms of wireless communication. We can talk about the electrical energy in terms of the power is voltage times current, or in terms of EM, we can talk about the Poynting vector, which is the electric field cross the magnetic intensity. So there's many ways of thinking about energy here. How do we think about energy in terms of molecular communication? Where does it come from? Well, it really comes from two things. So energy in molecular communication. So by analogy, energy in wireless comes from the electrical energy applied to the antenna. Similarly, energy in molecular communication comes from the molecules stored in the reservoir. So let's go back a couple pages here. So remember our reservoir right here. So that reservoir is where I store the molecules that get transmitted. And once they leave, once those molecules leave, they propagate by Brownian motion. Actually, there's no energy that's required in this process, at least from the transmitter's perspective. But the energy expended by the transmitter is the energy that's required to create this reservoir. So creating the reservoir takes energy. So we, in fact, must think about how energy works here, because otherwise it's a completely free lunch. If we just imagine that there was no energy at all in creating a reservoir, then it seems like molecular communication is completely free. But we know from analogy to nature, we actually know that that's not true. So it's obvious that communication has at least some cost. Organisms can't communicate freely or at will or at unlimited data rates. So there must be some cost associated with it. And the right way to think about that is in terms of creating the molecules that you're going to release into the environment. There's two ways to think about that. One is chemical reactions that create signal-bearing molecules. What do I mean by that? So again, if you create this reservoir of N molecules, and each one, there's a chemical reaction that creates it, and there's an energy E, EM, I'll say, energy per molecule associated with that, then the total energy required to create the reservoir will be N times EM. So very simply, energy scales linearly with the, if you like, the signal strength or the amount of signal. Second, let's suppose you were clever and you thought, well, I'm actually not going to create a reservoir by chemical reaction like this. So in other words, in order to load up this chemical reaction, in order to load up this reservoir, excuse me, what I'm going to do is I'm going to do something clever. I'm going to start in the environment, and basically, so the environment will consist of, let's say, it will already consist of a solution. Let's say it's salt water. In fact, let's say we're in the sea, we're in the ocean, and seawater is salty. And what I can do is I can start with seawater, which is salty. So let's use the color blue for water molecules here. And let's use the color red for salt molecules, of which there are a few. And what I'm going to do is I'm going to create a reservoir like this. So I'm going to pull as many salt molecules as I can and as few water molecules as I can. And I'm going to create this reservoir that's mostly salt. It's much more concentrated than the sea. So it turns out this is not for free. So the idea is create a reservoir using only changes in concentration. So you should already be able to see the flaw in this argument. If you know a little bit about thermodynamics, basically what we're doing is we're taking an environment that is at low entropy, and that is at high entropy, and we're turning it into an environment with low entropy. And that is, I mean, it's allowed under the laws of thermodynamics, but it in fact requires energy. Just like a refrigerator requires energy, an air conditioner requires energy. Anytime you decrease the entropy of the local environment, you have to use energy to do it. It turns out that energy, turns out that energy is called chemical potential. And it turns out, in order to move a molecule from a region with concentration C0, C0 to a region with concentration C1. So the molecule here is the molecule with respect to which we are measuring the concentration. It takes the energy required is proportional to so the energy to move one molecule is, excuse me, that's the total. I used EM for the total energy of the reservoir. So I'm going to use this just E for one molecule. That energy, excuse me, is not equal to, it's proportional to log C1 over C0. So if you do n moves, and assuming that those n moves don't change the concentrations very much, then the energy required to create the reservoir is again linear in the number of molecules. This is also interesting to note that if you're moving from an area of low to high concentration, so low to high concentration, this is positive, so the energy expenditure is positive. On the other hand, if you go back from an area of high concentration to low concentration, so that's basically evening things out, the entropy of the universe in that case is going up, you actually get energy back. And you can show that carefully constructing a transmitter this way actually does require thermodynamic energy. So continuing this discussion, going back to our table. Now, one thing that I'd like to point out is that this energy is actually very small. The constant of proportionality is very small. And in fact, I have shown that the total energy, there's a paper that I wrote, I will attach the link to this document later. But you can show that to create the reservoir, it can be done with an amount of energy equal to KT times the number of bits that it can be that it is used to transmit. Oh, KT bits log 2. If you think about KT log 2, this is called the Landauer energy. And this is the minimum amount of energy that any information bearing signal can contain. So 1 bit worth of an information bearing signal must have at least KT log 2, log 2 of E. Bits of energy. Energy per bit. All right, so this is actually a small amount of energy. That's the minimum, the theoretical minimum amount of required energy that's required for any information processing system per bit. So this is really small. So if I come back to my table here, the energy you require, let me put some notes. The energy you require is, it comes from creating the reservoir. And it is in fact small. Whereas the energy for wireless signals is relatively large. Oops. The other thing to think about, so this doesn't come with a free lunch again. you might look at this and think, gee, small amounts of energy are good. We like small amounts of energy. We don't like large amounts of energy. So maybe we would just use molecular for everything. But the real disadvantage comes with speed. Wireless is very fast, as we know. Molecular is slow. However, I will show you later in this course that it's slow in small systems, but if you consider systems to be large, then you can actually counteract the speed disadvantage. However, that means you are also expending more energy because the system is larger. So the way we think about things right now, wireless is large energy and fast speed. Molecular is small energy and slow speed. However, there's not necessarily anything fundamental about this. You could potentially have fast molecular communication system at larger energy.